moderating the session, which they'll be discussing the proposed new subtopics that came in from the RFI. So we have with us Mike Lowry, Mark Micire, and Bruce Jost.
Should we start now? So let me go into a little more introduction to my panel. As you said, Mike Lowry, he's a senior scientist or technologist for software technology for reliability. He works in the Exploration Systems Directorate here at Ames. He's had many years here at NASA. To my left here is Mike Micire. Mike is a research scientist in the Intelligent Robotics Group, and he's also within the Exploration Systems Directorate at Ames. And then to the far left here is Bruce Jost. Bruce is director of Small Spacecraft Systems Institute. He's also just recently was appointed the Mission Directorate Liaison for STMD, Space Technology Mission Directorate. So you'll be hearing a lot about him since he just joined the SBIR program. So Jim did an excellent review on the RFI process, and so the goal for today's meeting is to share with you 6 of the RFI proposed new subtopics. And we went through 291 that proposed new, and out of that, I had formed an RFI blended board, and it consisted of about 12 people. There were several MDLs, Mission Director Liaisons, 3 CTCTLs, and several subject matter experts. So we had a good team, and they went through every one of them, and out of that came out 18. Now, that wasn't work wasted because nearly half of those that we looked at, we scored pretty good, and we sent them off to the subtopic managers because we believe that some of the content of those that were proposed for new subtopics, that content could be included in the existing subtopics. So it enhanced the existing subtopics. So it was a good return. So with that, as you saw the list of the different 6 new subtopics, and we're going to start with Mike Micire, and he's going to talk about 2 proposed new subtopics for robotic systems for space exploration.
All right, so if we can bring up the next slide. Oh, I have a clicker? Got it. Awesome. So quick survey, just so I kind of know my audience here. How many people do we have that work in robotics or autonomy, machine learning, computer vision, or things like that? Okay, very cool. So a lot of the topics I'm going to describe here then should be pretty familiar to at least a decent percentage of you. So you see, in terms of NASA looking out over the timelines and the missions that we're looking at, as our missions get more and more complex, and as we are sending human beings deeper and deeper into space, the reliance on robotics becomes more and more important. Not only in terms of the robots being co-located, we always think of the robots being there with the humans, but you also have precursor missions where they are going out and setting up habitats and other things. But then you also have post-mission where if you're going to take the equipment and the robots all the way out to these far reaches of the universe, that you probably want to leave them there to continue doing the work that the humans may have been able to start but aren't able to persist. And so all of these are key needs that we see that kind of connect to that much larger kind of meta mission requirement that we're trying to satisfy. So the first one you see there, so machine perception algorithms for robust scene understanding and understanding of orbit environments. We have a lot of really great technologies that are out there right now in terms of scene understanding, feature point extraction, simultaneous localization and mapping, and most recently doing, that's normally called SLAM, doing SLAM with monocular vision. Those are all things that if we could do those under the robust and very complicated lighting conditions that we see in orbit or in other atmospheres, that having that capability would be very useful to robotics. Operator intent recognition. We see this a lot in autonomous automobiles where the ability for the machine to understand what the state of the human is would be hugely useful when we have astronauts and ground controllers working with these systems in very high-risk environments. Operator workload estimation. So right now, if we know we have so many pounds of payload that we need to lift into orbit, we can say, okay, we're going to need this much lift, And so therefore we are going to need this many of this class of engine to do that. And it's a very first principle engineering exercise to do that. When we talk about human workload and how much can we task that astronaut with during a given, let's say, hour of work, we don't really have those first principles in the same way that we do with the physics. And so the idea that you're able to say, okay, for this given task, that will be a 30% workload on that human being, it would be wonderful for us to have those kinds of metrics. Architectures for robust distributed semi-autonomous operation. We fully expect to have a mixture of folks in orbit. You could have people on the ground. You could have ground controllers back on Earth, and the ability to seamlessly switch back and forth and have architectures that support the ability to switch between each of those different modes of operation, and folks that are in very dramatically different environments to be able to control the systems that they're working with. Operator command augmentation and autonomous execution. One of the things that we constantly deal with is not having enough bandwidth, not having enough resolution. And so as you have less precision over your ability to control those autonomous systems, your reliance on the autonomy becomes more and more important, or the autonomy's ability to deal with those situations becomes more and more important. So any kind of systems that can contribute to that problem end up being hugely useful to our missions going forward. And then finally, flexible interfaces for rapidly programming reactive robot behaviors. The first rule of anything is that no plan survives first contact. And so we fully expect folks that we expect to be sending robots and autonomous systems into these missions and then having to reprogram them. And what would be wonderful is the ability for astronauts and ground controllers who are not necessarily dedicated programmers to be able to very quickly come up with scripts or other things that would allow that system to work in that environment robustly. And so making the autonomy smart, but then being able to guide that autonomy through the tasks that you need to do in kind of an ad hoc way would be very, very useful. So next slide. Or wait, I have the slide clicker. There we go. Okay, I'm going to let everybody read this one and summarize it. Basically, today we are living in a world, everyone in this room I'm sure has seen the craze that's going on with AR, augmented reality, virtual reality. We now have systems, so EMG, that's able to detect muscle movement and other things like that. This is especially for folks that work in the bioaugmentation, so exoskeleton type worlds, the idea that we have basically an EVA suit or a humanoid surrogate that is able to do the EVA would be hugely useful. Getting that human in the loop and making that very, very effective and making it such that the mission risk in using that type of system becomes lower will require a very close loop feedback to the human. And so what this paragraph is hopefully describing to you is that, through all the techniques that we have right now, that you're able to close that loop and make it very, very simple for that person to be teleoperating this surrogate human that's actually doing the EVA for them. And then the final point down there is, as we have folks that are on other planets, including Mars, one of the things that we're going to be doing is collecting a lot of data, and the ability to not only collect that data, but then be able to offload it, to exfil it back to Earth and have that cataloged, geotagged, and all of that becomes hugely important from a data management standpoint. And so that's it. So thank you very much.
Great.
You want to move?
Right, next slide then. Yeah. Stuck.
Anybody want to hear a joke?
Where's Rich? Rich, save me.
There you go.
Oh, that's the wrong one. Yeah. Those two charts in there?
No, there's two charts.
Okay. there more?
We could probably do feedback on that first one, perhaps, while we're waiting.
Sure.
If they need to upload. It looks like it might be the wrong slide.
Sure.
All right.
You go ahead.
I could add a bit too.
Yeah. Can't hear you.
Sorry, I can't hear you. Can we get the mic turned on?
Does the autonomy previously described? Can you hear me?
There we go.
Yeah. Does the autonomy include drones? Autonomy for drones?
So I would say that a lot of the focus, as you saw kind of from the themes here, the two biggest themes are more general autonomy. So drones would apply in that, especially with a lot of the systems that we have right now, you're dealing with multi-agent systems. Especially when we start talking about, swarms and other things like that. So the ability to have multiple robots that are coordinating their activities and stuff like that you could work that in the context of swarm, and that would be, or context of drones, and that would be directly applicable to the kinds of systems that we're talking about. The other thing there is with the drone systems that are out there, you also probably saw a theme here where there's a lot of what is kind of a whole subfield of robotics called human-robot interaction. So what we're not going to do probably is to train astronauts how to have two gimbal joysticks in each hand and do line of sight flying of these things. Those systems are going to need to be robust on their own, and your ability to command them, to task them, to be able to give them jobs to do, that again can not only has huge commercial applications in the commercial drone world, but if you could solve that problem there, that ends up being hugely beneficial to kinds of missions and the other robotic systems that we would definitely be using for NASA's applications.
Okay, so what we continue on, we'll answer questions later, so.
Awesome.
So just swap through.
Okay, additive manufacturing in space. So I believe I know that there was a subtopic in this area in the small sat topic last year. I managed that. Yeah, for this one. So okay, and so there's kind of some thinking already along these lines. Additive manufacturing space has a lot of different benefits that that come along with it. The first being is that we have these very powerful rockets now, the SpaceXs and the Heavies and the Falcon 9 Heavies and the Atlases that can lift a lot of mass into space, but we're going to quickly be limited by the fairing size and what we can put underneath the fairing. Someone told me that James Webb will probably be the largest single most thing ever launched on one launch because of just the folding and the complexity of it. There probably won't be a bigger diameter telescope like that unless it's assembled in space. So additive manufacturing has a similar kind of benefit that you can aggregate and create things in space that might be very difficult to launch in one go, but also maybe something that you can do in space when you're not really sure what you're going to do. If I don't know what my requirement is, I don't know what's going to happen, I can still take materials and equipment with me, and then when the situation arises, then we'll make the tool, the widget, the aperture, the radar, whatever the thing is that we need to have done in space. So that's kind of the background for it. Now this particular subtopic is talking about actually doing chemical processing, breaking CO2, harvesting water, doing some physical kinds of things that in situ resource utilization types of things. So how do we attack those? Different chemical processes need to happen. We can't take everything with us, so we're going to have to live off the land. So that's what this subtopic is looking at it. There's also things, this kind of ties into the human factors stuff. You need to have oxygen for people. You need to have water for people to live. So that's what this one was picking up on. The second one is looking at some very small structures, nanocomposites in space. Again, using the type of technology that we have on the ground. You're seeing a lot coming out of the maker community. How can that be leveraged to create structures or recreate structures, if you will, if you could destructively, or how to melt the structure and recast it or reprint it. This would approach that kind of issue. So the nanocomposites is a little bit of a twist here from the stuff that we've seen before. Typically we're just printing things. They're printing things on space station right now. There's some missions I know coming up to try to print structures coming out of CubeSats, for instance. But this gets down into the very chemical arrangement of the atoms in the molecules. So that's kind of the back. That's kind of the back to, or the basis of the two things I was going to talk about. And I guess we'll do questions at the end, right? Okay.
Now we'll see if you got your slides.
Oh, okay. This is teleoperation. While we're waiting for them, who here has experience with electronics, computer hardware, memory management? Great. And who's had experience with doing that in space? One fellow back there too. Thank you so much. So here's the skinny. We've seen enormous advances with Moore's Law, on the order of a factor of 1,000,000 since the introduction of the first microprocessor. But when we get out into space, we have a couple of difficulties. One of them is that radiation is equivalent to trying to do your processing in a very high heat environment. If you look at the error probabilities for integrated circuits, they go way up. With temperature, every single radiation hit, whether it come from the sun or the background galactic cosmic radiation, is basically a very high temperature ion. It can throw a single event upset, and then everything goes haywire. Now, the second thing is that space is a very limited environment. Now, we're trying to make it to be a much a lot larger market. Small spacecraft and CubeSats are partly one way of doing that. But because of that, we're facing very, very high expenses right now on the processor side through the integrated circuits that support a processor and on into avionics, or they could be sensors, they could be the infrastructure that supports the I/O from the sensors to the processors. And because of that, we're they're very expensive. The RAD 750, which is a mainstay for doing computing on a small spacecraft of the 200 kilogram variety, is roughly $1,000,000, and it goes at the speed of my MacBook in 1998, so that far back. So a question that came up is, can we develop chipsets? Can the small business community help us develop chipsets that support processors and are immune to, or at least tolerant of, radiation? And that's a very substantial challenge. It is one that has been met in part by NASA on the processor side, and the way that that has been done has been to develop circuitry that is robust to radiation. Sometimes it's robust to radiation because you have fault tolerance built in. Sometimes you make fatter transistors that can sustain a radiation hit. DARPA actually has developed a circuit library, and if you use that circuit library together with the standard ways of developing chips, going from the register's transfer level, that is one approach, and it is able to also use traditional foundries that you can go anywhere in the world, take your tape out, go to the foundry, and then get back these chipsets. And that might be something that some folks here in the small business community would like to engage in. So if you've ever been designing integrated circuits, you have some capabilities in-house to do that, this might be a topic that you want to go for. There might be other approaches to hardening modern chipsets that support processors and avionics in general. NASA and DARPA certainly don't have a lock on that, and so perhaps you have some feedback on technology that we should be thinking about in order to do that. So the questions that I hope that I'll be able to field are, what are some of the approaches, some of the technologies, and some of the interest, if any, for providing chipsets that are radiation tolerant and low cost, as opposed to those chipsets that have to be done by, say, BAE or Boeing or something on very specialized foundries that become very expensive because they're limited lot sizes. And a real big target of opportunity here is to go after small spacecraft or CubeSats, probably on the order of 6U and above. And if we can do that, if we can bring down the cost of the avionics, I think that that market that we're looking for in space both on the government side and commercial use of space, could expand considerably. Okay. Now, second one is that there is a National Academies report called Achieving Science with CubeSats. And they point out that swarms and distributed systems of, I should say, small spacecraft, they're enabling for remote sensing, exploration, and science applications of interest to both industry and government. Here's a fascinating application. Do interferometry of a star and blank it out, and you're able to look at the atmosphere of the planet that's next to it and do spectroscopy on it. That'd be fantastic. There's a lot of applications. That's just one application, interferometry. If you could blanket a whole planet and be able to take real-time readings of the weather, of aspects of the ionosphere perhaps, you could do incredible things and advance our understanding of planets and of the solar system. But in order to do that, we need new technologies that are able to command swarms, that are able to help them coordinate. That includes communication between swarms of small CubeSats, and we can really start looking at some mission architectures. Just a little point here is that traditionally the smallest size of a spacecraft that you can get is limited by the physical aperture that you need for the kind of remote sensing you want to do. But if you know anything about something like phase arrays, you distribute your sensors, small sensors over a large area, you can get that same effect. So now if we're able to get these technologies, we can do missions that previously would require huge apertures, huge physical dimensions, do that through distributed swarms, do it very cost effectively. Could you contribute technologies to make that a reality? Thank you.
So we'll solicit questions. Yeah.
It's for you. What orbits are we talking about here?
I'm sorry, can you speak up a little bit?
What orbits for the spacecraft and technology that you're looking for?
Are you talking about for the avionics, or are you talking about for the distributed spacecraft?
Either or.
Okay, well, it can really vary. So you could, for example, have a set of orbits that are suitable for, let's say, monitoring the magnetosphere. You could have ones that are for, that could be a polar orbit on Earth. For monitoring Mars, unless you try to do distributed weather sensing, real-time weather sensing, be able to correlate them all together, then you probably want to have orbits that blanket and have coverage from whatever aperture your sensors have for the whole Martian surface. So the orbits have to be designed with respect to the specific ones in question. Now, I think perhaps you were asking on the distributed spacecraft about what is the station keeping that's required. In other words, like for interferometry, you typically have to be within a quarter of a wavelength of the light or of whatever photons that you're using. So that's a very strict station keeping. Other times you might, for example, want to have a set of satellites that are going in an orbit, coplanar, and you need to make sure that their spacing is sufficient. So for example, if you want to see effects of gravity as it varies over the Earth's surface, you want to be able to make sure that those spacecraft are tracking each other in time, and then you look at the variation in the distance, and you're able to deduce what's going on with the gravitational field. Now let me flip that over with respect to the avionics. Up to the International Space Station, the effects of single event upsets are fairly mitigated. SpaceX, for example, was arguing that it should be able to use commercial processors going all the way up to the space station as long as it had redundant configurations. As you get into the Van Allen belts, you get into deep space, the radiation count goes up tremendously, and can vary too. When the sun throws a solar particle event, the radiation can be so intense that it would fry astronauts that were not enclosed. And they did calculations for Apollo on the probability of having a big corona discharge, for example, and they thought that it would be within acceptable risk. But for a long mission, it can be extremely high.
No, for a long mission, are you talking like a geo, 10, 20 years, or more focusing on real, maybe a few years? I was just, with respect to like LEO, GEO, MEO, or polar orbit, and orbit mission duration, what is the focus of these topics?
Okay, good question. So the question is, what is the focus of these topics for the duration of the mission? So a little bit of background there. With respect to radiation, it used to be the case that for circuitry that had a lot of silicon dioxide in it, and that was the standard way of doing manufacturing with CMOS for a long time, that silicon dioxide would become a pocket, and any ionization that comes through would land in there and start becoming a charged capacitor, and that would, of course, basically blank out. So that's total radiation dosage. Nowadays, if you're able to do that manufacturing on top of sapphire, then your total radiation dosage problems goes away significantly, and then the effects of radiation become temporary. If you happen to land in a portion of the mission that is not time critical, maybe not a problem at all. But if there's some kind of critical maneuvering or a critical communication and you miss that because of a single event upset, then you got a major problem. With respect to the differentiations on the orbit, as I was kind of alluding to with reference to the International Space Station, in LEO you can sometimes get away with it. As you go up in altitude or you go outside of the Van Allen belts, then you become, the radiation dosage become much more significant. And as you see, the kinds of missions that we fly outside, they're almost always done nowadays with radiation hard processors like the RAD 750.
So another comment just generally as you guys are thinking through this, because you just saw 6 very different subtopic ideas, some of which were kind of what I would describe as like capability building or market stimulation type subtopics, like this one, how do we do more swarm technologies for CubeSats, some of which were pretty specific around particular technologies or problems that we could be solving at NASA. So as you guys think about these 6 that are very different, maybe you're only interested in the robotics piece or you're only interested in the radiation hardening piece. It's also good feedback to say whether or not some of these feel too specific to you, or some of these feel too broad, or how does this really have a market beyond NASA? Though any of those kinds of insights, it's not necessarily just a deep dive technical conversation right now either. Sure. Those types of observations, questions, comments are also the types of things that would be welcome in this dialogue.
Okay.
It's on.
Testing. There we go. Mute was on. On the issue of radiation hardening circuits, do you feel that repeated flights through a GTO orbit would be sufficient for raising a TRL up to 9?
That's a very interesting question, and I'm going to have to plead ignorance. What do you mean by GDO?
GTO, geosynchronous transfer orbit. In other words, a big parabol.
Right. So certainly the TRLs can go up high. We can get heritage from previous flights, and that's just a general consideration. That also indicates that if you're able to get onto some CubeSats, and we hope that some of the small businesses here will be able to get their technologies onto small businesses, you get heritage on that small business and on that small CubeSat, and then you can go on, say, to swarms or to larger spacecraft. So yes, indeed, repeated ones. I will also remind you, though, that when we talk about TRL 9, you're well outside of phase 1 and phase 2 SBIRs. It's just a point there.
A lot of the current machine learning and autonomy research is very, very compute intensive. I know that you just mentioned that the compute capabilities are very limited. So So could you just give us a quick overview of what kind of compute capabilities, memory, storage, bandwidth we can expect, let's say, over the next 10 years? And then, is there an interest in mathematical methods, maybe, that could squeeze a lot more out of the existing compute infrastructure? And that's not the way research and industry is currently going. We have all of the GPU cycles that we can burn versus you may not.
Can I? Sure. Yeah. So big distinction between doing the machine learning and then running your neural net or equivalent. The neural nets can be blindingly fast, and I can tell you that there are technologies that are coming, at least for Earth applications, that is going to really blow out the current GPUs, for example, which are seen to dominate. As you go towards doing the learning itself, learning in situ, running deep learning or something like that, you are indeed correct. Those require a lot of compute capabilities. There are some technologies that are coming down the pike, but you might want to think about a distinction between when you do the learning. Is learning being done on a small processor capability, or is it being done back on Earth, or maybe some sort of spacecraft that is the mothership, if you will, versus actually running the neural nets?
Thinking of that question, you didn't speak a lot about storage. Where is NASA relative to storage? Is that a bottleneck as well? And a related question, other architectures, computing architectures like FPGAs or related technologies, are you considering those as well?
Yes, we are considering those technologies, and I think that this interest in in those technologies and what small business could do is very good feedback to us right now. The High Performance Space Computing Project, and I think this is public domain, did make a trade study, determined that a CPU was the highest relevant that NASA should be funding, but these things that you mentioned were all in consideration and were seen as valuable, just not as top priority to a main processor CPU.
On the subject of in situ resource utilization and 3D printing, we are all aware that we can do this. We can take in situ resources, process them, pre-process them, and then make something with them. But I've seen very little discussion about how we're going to verify and validate that what we actually make is actually going to work and be reliable. Because what we end up with is something that we need, or we wouldn't go to all the trouble of making it, but we're going to be adding risk because we are not certain that what we made is actually going to hold up to its use.
So true, and there's one distinction I think that's critical to that is that when you talk about verifying and validating things, the way we do it now is we do it on the ground because it has to survive the launch environment and that sort of thing. That is not entirely the case if, for instance, you want to make a long Gossamer truss that's on two ends of an interferometer that's a fixed distance between the two. You can make that, if you could make it in space, but you don't have to make it to the same sort of mechanical loads and requirements that it would have been done if it was launched on Earth, even in pieces, perhaps. I would say. Precision does have to be high, and you're right. So are we printing precision parts? I think we're getting there. I'm kind of just vaguely remembering. I know groups that in Huntsville are printing nozzles and things that need to have very nice surface finishes on them, and that sort of thing to be used as rocket nozzles. So I don't know that we're there yet, but yes. So the precision needs to be addressed. And then there could also be confounding effects of trying to do something in microgravity or in vacuum that you normally didn't. You don't have the problem on the ground. So I think there's a lot of area there for research.
Hi, I'm interested in if you could explain the subtopics and what the technological gaps are in the area of human performance and health, and what is needed in terms of monitoring psychological health of the astronauts as they go out there?
It's probably closest to the one I had. And this is not my area of expertise, other than the one that I described, especially. As you start looking at workload, and when are you placing, in this context, the robot operators or the operators of the semi-autonomous systems at their maximums? Are you able to detect that? We have, between EMG, EEG, and all of the wonderful tools that we now have available to us, I would say that one of the biggest things that I repeatedly hear that we need is the models. So the ability for us to ground out to almost a first principle analysis of, okay, if a user interface with this number of features that need to be monitored is placed in front of one person, where does that place them in terms of all of the different biological stressors and that may come into play there? And let's just say I was surprised to find that we didn't have a lot of those tools. So I would say that would be one of the main focuses there. Yeah.
Okay. So just a question about the autonomy side, the machine learning side that you talked about. So my question to you is that, given that the mission is far away from the Earth, and you may not have, no matter how well you are trained, you have trained your machine learning things for your lot of different autonomous jobs. Given that you are far away from the Earth and you don't have really time and resources to retrain on site, because all the computing is back on Earth, do you consider that as one of the primary challenges to enable for your autonomous systems?
Sure, and I would say that right now for machine learning, whether that be whether it be in space or be on the planet, one of the big things that you see the autonomous automobile companies dealing with is the fact that it is very, very difficult with a lot of these machine learning systems to do the V&V, like we discussed earlier. So what do your edge cases look like? What does that system do when it encounters sensor input that it has never seen before, that was not in its training set? That is a quandary that not only NASA is having to deal with, but you hear DoD dealing with that a lot, especially in terms of weapon systems. The autonomous vehicles are dealing with that because now we have robots that are effectively carrying human beings around in the world. So the short answer is yes. Any technologies that could be brought to bear on that aspect of machine learning would be hugely valuable. And I will add, would not only benefit NASA, but would just have enormous commercial impact such that solve that for us. And I don't think you're going to have any problem finding other customers that are going to want it too.
In regards to telepresence in robotics, is the ultimate goal to have the astronauts in space be able to control them, or from Earth? And then on top of that, most of the SBIR, you're proving feasibility, and in phase 2, you're supposed to be able to test that. How exactly are you supposed to convince NASA that you can test these systems when you can't get your autonomous system up into space to test that during a phase 2 SBIR?
Sure. So to the first part of your question, the answer is C, all the above. It really depends on the mission. So we have here the group that I work with at Ames, we have done operations where we had astronauts on the ISS controlling a rover that was running around in one of our little Mars yards that we have out here. For especially precursor missions, that's hugely useful. We know that when you are going to have folks in those kind of environments, that you are going to want to have ground controllers also assisting them. And so the ability to not only work from orbit to the surface of Mars, let's say, that can be a relatively high bandwidth link given infrastructure and other things that we can put in place. The time delay that you deal with from Mars to Earth, depending on where it is in its orbit, can be significant enough that for ground controllers that becomes a difficult task to deal with. We deal with that every day with the robots that we have up there now. Rolling that all up into a kind of a meta mission concept where you're able to move back and forth between those different modes of operations becomes very, very important. And that was actually what I was, the one point was hinting at with respect to architectures that allow you to move within these temporal modalities, bandwidth modalities, and other limitations that may be kind of your trade spaces there. And I'm pulling a blank on your second question. I apologize. What was the? Right. So I would imagine, and we've had, we have a couple of SBIRs that we're working with right now, that you're right. Your phase 2, you are looking at proof of concept type things, but there are opportunities for flight there. We've worked with a lot of small companies, especially, and I'll let you speak to this, Bruce, with the small sats, where there are flight opportunities for those kind of technologies. We've had a lot of equipment go up to the International Space Station, especially out of our group. And so if there, let's put it this way, if there was an opportunity, and if out of that line of research that you were working, that we were able to see enough value in that research line, we certainly have the capabilities to try to make that happen for you.
Yes, just point out that there's a sister organization within STMD that is focused in on small spacecraft itself, and the goal of that program is to get that flight demo that you talked about, that flight data. Now, does it apply to this particular case? It may or may not, but small spacecraft are robots if you squint your eyes the right way. So yeah.
So is your computing architecture for small spacecraft as well as robotics considering just being not vulnerable to cyber attack?
Wouldn't that be nice?
So I guess if I could rephrase my question, what I'm asking is it appropriate subtopic to assume that a proposal with a solution to a cyber defense, would that be funded? Do you think that would be? I mean, didn't mean to ask it that way, but I mean, I think I really haven't seen anything from NASA addressing that problem with regard to. I mean, you look at it from more of an IT perspective versus a mission perspective, and I think that ought to be looked at pretty seriously in the computing architecture.
So let me try to rephrase the answer then a little bit and say that cyber is hugely important to these kinds of systems, and I'll say especially with a cyber a system that is robust to cyber attacks is probably also robust just in a general design and infrastructure standpoint. So the good coding practices and other things that you would put in place to make sure that a lot of, frankly, the ways that cyber is able to leverage its way into those systems, that those are the same practices that we would want to have on our spacecraft systems. In the past, we used to have the luxury of folks not being able to have access to satellite capable antennas and transmitters and other things like that. We actually don't live in that world anymore. It's actually pretty easy to surf eBay and find equipment that will allow you to talk to things. And so, long story short, that will, in the future, in the very near future, become more and more important to the kinds of systems that we're flying.
I'll add quickly to that. Consider where the bulk of human space is. For example, the International Space Station is called international for a reason. Those people that we're working with are our friends, but there's sometimes things that you would rather not get to the Russian side of the space station, for example. If you look at the space maps that we have going in the future, most of them are going to be global endeavors. They're going to involve international partners, mostly friendly, but once again, there's going to be things that you do not want to get out to your international partners. So I think most of the architectures going forward for human space will involve a necessity for some aspect of cybersecurity.
There's a virtual question directly related to this one that's up. What watts per kilogram targets do you have for the swarms? And remember, this is an RFI proposed subtopic, so this is a question for discussion for the audience. What watts per kilogram would be the targets for these swarms?
So we're looking at spacecraft designs that are on the order of maybe 10 to 20 kilograms that can generate 60 to 120 watts. Looking for my MMA friend around here, but it's on those kind of orders for the smaller spacecraft. I don't know. I wouldn't know how to hazard a guess for things that are larger. Although I do know that some of the solar electric propulsion systems that we're looking at want to be able to generate kilowatts of power to be able to move significant masses around significant distances.
Thank you. And we'll take one last question from the audience, and we'll break. Go So I actually wanted to expand on the cybersecurity. We are actually funded to do a cybersecurity solution for small space aircraft, so we can talk about that. But beyond that, how do we actually make sure these swarms are resilient? And that will be both from a cybersecurity perspective. It would be, you know, a node can be compromised, or a node can actually get outside its parameters and be operating in a way that it's not supposed to. And now if that node was in charge of running an antenna for you, your antenna is never going to be what you would like. So there might be more work that we may need to do in this space to design these resiliency in mind first, with the communication and the backbone as we apply them to missions. Are there thoughts about that?
Yes, and that they have been in consideration with some of NASA missions, but we certainly have not exhausted the technology opportunities. I would say that robustness and resiliency is one of the chief challenges. As you point out, you can have dropouts because some particular element of the swarm goes, as you say, outside of its parameters. How do you fill that in? How do you fill that in a way that perhaps maintains the at least some partial of the sensory monitoring that you want to do? And of course, it can take everything from, let's say, switching the communication protocols. So someone, a particular spacecraft that was a leader, now becomes a follower, for example, or just drops out entirely. A new one has to be promoted as leaders. So the resiliency protocols for distributed systems actually are a key to the distributed spacecraft technologies and other ones that are within the overall NASA SBIR.
I'd like to ask a quick question. How close are we to entangled photons on small spacecraft from the U.S.? I mean, the Chinese have demonstrated that now, and it's theoretically it's unhackable, right? Is the small business community at all interested in something like that? If you are, let's talk.
And I'll just add, one of the wonders of Swarm is the combinatorics. The really tough part about Swarm is the combinatorics. And so I would actually argue for a lot of the Swarm solutions that we're seeing that are out there, if we are going to argue about robustness and other things, that has, in my mind, has to fall back to the first principle algorithmic foundations that you're building those systems upon. That you really have to look at that at a very fundamental mathematical model level to have those kind of systems be really, really robust in those kind of environments for the types of situations you were talking about.
Okay, thank you for our panelists. If you want to have more RFI feedback, please speak with Bill Toscano. He'll be available for one-on-ones. The rest of our panelists, thank you for joining us and sharing the RFI feedback. So right now we have about a 5-minute break if you want to get some